Hey, anatomy students, welcome to day 2 of the respiratory system. Last class period, we talked about the anatomy of the system and the flow of air of the system from the nasal cavity all the way down to the alveoli through the bronchi for gas exchange, respiration gas exchange. I wanted to start day 2 of the respiratory system with a viral picture that showed up almost a year ago um, on Twitter and other social media outlets. And you can probably guess what you're looking at here. And this is last year's Mount Everest climb, the long line to get to the peak of Mount Everest. And very interesting that people do this every year. And I really like the quote Everest, the movie, is actually, I think, a pretty good movie based on a true story of some people who tried to climb Mount Everest. But simply, human beings simply aren't built to function at the cruising altitude of 747. That's an airplane. Our bodies will be literally dying. And in 2019, 11 people did pass away. I believe Nepal gave out somewhere over 200 or 300 permits for people to climb last year. So some people did make it. 11 did not. I did read the bios of the 11 people that passed away on their climb, and interestingly, I would say half of them died in their sleep in their tent as they either had just reached the peak or were camping to get to the peak. And most certainly, everyone of those 11 people would have died due to some sort of oxygen distress to the body and a lack of homeostasis in the body. Mount Everest, why is it so difficult to climb? Well, we'll answer that question at the very end of today's lesson about gas exchange. And remember, the official name for gas exchange is respiration. Breathing is pulmonary ventilation. So I wanted to show you this first, that the blood in our body actually has two different colors, slightly different shades of red. The dark red blood is more of the what the color of deoxygenated blood would be. And when blood is oxygenated, it becomes a slightly brighter red color, more scarlet red. And that happens in the pulmonary circuit. That happens as oxygen diffuses through the membranes of the alveoli into our bloodstream, and carbon dioxide diffuses out of our bloodstream into our alveoli, those air sacs we talked about in class 1. Now, the timing is important. So alveoli, grape-like sacs, we have millions. And as a red blood cell travels around the air sac, you can see that color change. And I'll go backwards a little bit. But the timing is more important. It takes about 3/4 of a second for a red blood cell to travel past an alveolus. So it's very quick. In that time frame, it takes 0.25 seconds for the red blood cell to pick up its oxygen. And I kind of compare it to filling up your gas tank. So you go down to the speedway, and for most of us, it takes 5 minutes or so to fill up our gas tank. And it's the same thing here, just a quicker scale, where it takes 0.25 seconds for one red blood cell to fill up its gas tank, in this case, with oxygen. So there's about a half second leeway there to make sure that a red blood cell gets as much oxygen as possible. And that's kind of the basis of today's lesson, is picking up that oxygen and moving it through the body. Here's what that looks like. So capillaries surround our alveoli. These little sacs are the alveoli. We have millions. And as I just mentioned, to go from one side, for a red blood cell to go from one side of the alveolus to the next, it takes 0.75 seconds, but it only takes 0.25 seconds to pick up the oxygen. Here's what the inside of the alveoli look like, and you can see, kind of taking that last picture and looking inside, blood vessels, capillaries surround the alveoli, so you can see the red blood cells, and the red blood cells will be the main thing that would pick up the oxygen. So we breathe in, and oxygen travels all the way to the alveoli and then diffuses into our capillaries, and our red blood cells pick them up, and vice versa. Carbon dioxide is dropped off and diffuses into the alveolus so that we can breathe out that carbon dioxide. And you can see just some stuff we've learned already. There are macrophages in our lungs, and macrophages would be there to clean up debris and to protect us. These other types of cells we're not going to worry about within this unit. So let's move on to pneumonia. And you've probably heard of pneumonia. Some of you have had pneumonia. And here's why pneumonia can be so damaging to the body and to homeostasis. Because of the nature of pneumonia, it takes longer than 0.75 seconds for a red blood cell to fill up its gas tank, to fill up with oxygen. And the main reason is mucus. So if I go back and you imagine that there is mucus all inside this alveolus, that will slow the ability for oxygen to diffuse into our bloodstream, and that would impact the entire body. And lead to body tissue oxygen deprivation, which would definitely impact the homeostasis of every system. Since it is relevant, we'll talk a little bit about COVID-19 pneumonia also. But when people get pneumonia, oftentimes, I would say the most common type of pneumonia is bacterial pneumonia. But you can also get viral pneumonia, as we're seeing with COVID-19. And it basically, we said it impacts the entire body. Fever, chills, dehydration, fatigue, loss of appetite, malaise. You probably know what that means from Spanish class. Just feeling bad. Respiratory wise, you have to breathe faster to try to get more oxygen into your body, but your breathing is more shallow because you have mucus issues, can lead to shortness of breath. You might have some wheezing. And then oftentimes we would do a chest x-ray to diagnose it, or a scan of the chest to diagnose this. And what we said last time, the anatomy of human lungs, we have 5 lobes, and oftentimes pneumonia, it is isolated to 1 or 2 of those lobes. You may have heard of double pneumonia. Double pneumonia is when you have pneumonia in both lungs, so the right and the left lung, and that's obviously a worse situation when you have the double pneumonia. Here's a chest x-ray of probably bacterial pneumonia. And really what you're supposed to see is darkness in the lungs on an x-ray. And that darkness just indicates that there is air, gas in the lungs. And in this particular x-ray, you can see there is a white patch over here in the circle, which would be indicative of pneumonia and the mucus that is produced by the body when we get pneumonia. COVID-19, this is one of the early chest scans of a COVID-19 patient, and you can see 3 different areas of pneumonia indicated by the arrows in this picture. And we're seeing with COVID-19, a lot of people get the pneumonia at the end of the lobes. So the lateral sections of the lobes of the lungs is where the pneumonia is showing up. And very similar to the previous picture, this is a scan instead of an x-ray. And you can see not only the mucus buildup, but probably some damage to the lungs that will take a while to repair itself. So, how is oxygen transported by blood? And I think we kind of answered that already, but we want to get a little more specific. Red blood cells are made of the protein hemoglobin, and 98.5% of the oxygen that is carried in our bloodstream is bound, literally bound, to the hemoglobin of our red blood cells. 1.5% of the oxygen is just free floating in our plasma, so that would be a minuscule amount. We have to carry oxygen with hemoglobin of our red blood cells. And this is a very cheap red blood cell that I created through some PowerPoint art. But what I just said, hemoglobin is carried by red blood cells, and every hemoglobin can carry up to 4 oxygen molecules. And there would be thousands of hemoglobin proteins made up, making up that red blood cell. All right, some physiology. This is a very important physiological curve for the human body. And I want to talk about it in depth in that to understand a graph, you have to understand two things first. You have to understand what the x-axis is saying, and then you have to understand what the y-axis is saying, and then you have to understand what the actual line is saying. So let's hit the x-axis first. And it says down there, oxygen, x-axis is always the horizontal axis, the oxygen partial pressure, otherwise known as PO2. So this would be an environmental number. How much oxygen is in the air? And you can see that the graph goes all the way up to 120 millimeters of mercury of oxygen in the air. And that's kind of where sea level on Earth would be. That's the amount of oxygen in places like Miami, the beach, any beach on Earth. So a lot of oxygen at sea level. And then once you start going to higher and higher elevations on Earth, the amount of oxygen in the air severely decreases. So again, x-axis is the amount of oxygen in the environment. Y-axis is the vertical axis, percent saturation, measured as it said, a percentage. So this would be the percentage of oxygen attached to your hemoglobin. And for most of us right now, that number should be near 100%, if not 99%, 98%, would be indicate homeostasis. As you start getting lower and lower with the oxygen in the air, you can see that the oxygen attached to hemoglobin starts decreasing exponentially. And for most of us, we would not notice issues until we got less than 95% usually. For some of the COVID-19 patients, I've heard some percentage saturations in the 70 percentages with the pneumonia, and that would be an issue. When you start dipping below 95% is when the body will start getting impacted. And we'll apply this to Mount Everest here in a second. So what's the graph saying? As oxygen in the air increases, more oxygen will bind with hemoglobin in your body. And we can go the other way around also. As oxygen in the air decreases, less oxygen will bind with hemoglobin. And remember, the goal is to get constant supplies of oxygen to every cell in the human body. Why? So we can make ATP, that great energy currency that our bodies, our cells need a constant supply of ATP. So why is it so difficult to climb Mount Everest? And here's another picture. It's pretty simple, I think. There's not enough oxygen. There's not enough oxygen in the air. So it puts a tremendous stress on the entire body. So let me give you some numbers. Last time we said Yorktown is about 2 football fields above sea level. So the amount of oxygen where you're at right now is about 160 millimeters of mercury. So if you go to the graph again, 160 down here would be all the way over here by this arrow. So again, we have enough oxygen in the air. Most of us should be 100% saturated or 99% saturated. And that would lead to homeostasis. The elevation of Mount Everest is just over 29,000 feet. And if you do the calculations, that's about 5.5 miles above sea level. So the amount of oxygen at the peak of Mount Everest is 60 millimeters of mercury. So let's go back. 60 is right around this region. So if we guesstimate, that appears to be definitely less than 90% saturation of the body. I would say most people would go somewhere between 80 and 90%, and that would lead to some physiological conditions at the peak of Mount Everest. Passing out, cyanosis, turning blue, just to name a few things that someone might experience climbing Mount Everest. Let's go to an airplane. At cruising altitude of that 747 mentioned in our first quote, 40,000 feet is the normal cruising altitude. So when you look up in the sky and all you can see is a white contrail and you can barely see the airplane flying above your home, that's 40,000 feet. And there is only going to be 30 millimeters of mercury of oxygen at that elevation, which, if we go back to the graph, I mean, we're looking at probably 60% saturation if one of the windows blew, etc. So, airlines counteract this by sealing the door. So as soon as everyone gets on the airplane, they will seal the door shut. The windows are double glassed to try to prevent a loss of oxygen. And most airlines will have 125 millimeters of mercury of oxygen inside the plane, which will get everyone on that plane to around 100% saturation of oxygen. If one would happen to be on an airplane and you would lose cabin pressure, you would see a situation where, and I need to change this, these gas masks would drop down from the ceiling. And they kind of train you how to use these when you first, before the plane takes off. And I will tell you that if you're at cruising altitude 40,000 feet, the only way these things will work is if you have a tight fit to your face. They will be useless if they're not tightly fitting, because there's just not enough oxygen in the air if you have any spaces between the mask and your face. So, not to scare any of you, but if this ever does happen, you want to make sure that the masks that would deliver oxygen to you form a seal with your face until you can get to a cruising altitude that's a little bit lower and you can gain some of the oxygen from the air. And that concludes our gas transport PowerPoint.